Have you ever wondered how a machine actually thinks? I mean, not just calculates, but genuinely reasons its way through a problem? Well, today we're cracking open the instruction manual for machine thought. We're talking about a system called first-order logic.
So, this is the big question, isn't it? We see AI doing all this incredible stuff, solving these crazy complex problems. But how? What's going on under the hood? It's not magic, I promise you. It's a very specific and incredibly powerful language built from the ground up for pure logic.
And that language is first-order logic, or FOL for short. The source material calls it the workhorse of automated reasoning. And honestly, that's the perfect way to put it. It's the engine that really powers logical thinking inside a computer. So let's pop the hood and see how this thing is built.
To really get a handle on this workhorse, we've got to start with the absolute basics, its fundamental building blocks.
It turns out, first-order logic really stands on three main pillars. First, you have syntax, which you can just think of as the grammar. Then there's semantics, which is all about the meaning. And finally, you have the proof techniques. That's the engine that puts it all together and makes it go. Let's start with the grammar, the syntax.
All right, first up is syntax. This is all about the rules of the road, how to build a logical sentence the right way.
Think of syntax as the strict grammar police for logic. It's a rule book, and its only job is to make sure every statement is structured correctly. It doesn't care one bit if what you're saying is true, only that it's formed properly. So all X are Y gets a green light, but all are XY? Nope, that's grammatically wrong, and syntax throws it out. It works just like grammar in any language you speak. Okay, so a sentence can be perfectly structured, but still be complete nonsense, right? A well-formed sentence is pretty useless without meaning, and that brings us to our second pillar, semantics.
So if syntax is the grammar police, semantics is the fact checker. Its job is to take our perfectly structured sentences and see if they hold up in the real world, or in what's called a model of the world. For instance, a machine might read the statement, "All birds can fly." Semantics is the system that checks that against its knowledge and says, hold on a second, what about penguins? It's the part that determines truth.
So to boil it all down, syntax gives you the structure, the rules for how to build the sentence. Semantics does the truth check. It gives that sentence meaning. One is about form, the other is about fact. And a machine absolutely needs both to make sense of the world.
Okay, so we've got the rules, we've got the meaning. Now it's time to fire up the engine. This is the really cool part. This is where proof techniques come in and let a machine actually discover new things all on its own.
And the star of this show is a powerful method called resolution. It's a technique built specifically for computers to use. Imagine you tell a computer two things. First, Socrates is a man, and second, all men are mortal. Resolution is the logical process that allows the machine to automatically connect those dots and conclude, aha, therefore Socrates is mortal. It's the absolute core of how most automated systems prove things. And this whole machine-first approach is incredibly powerful. It uses really advanced mathematical methods, these things called calculi, to chew through incredibly complex problems. This isn't just a theoretical exercise either. This stuff is the foundation for actual AI programming languages, like Prolog, where you literally build intelligent programs by feeding them a set of logical rules.
So let's bring it all together. How does this whole framework, syntax, semantics, proofs, actually become that AI workhorse we started with?
This chart really lays it out perfectly. On one side, you've got the building blocks of first-order logic. On the other, you've got the real-world tech it creates. So the ability to define rules and relationships, that directly leads to logic programming languages like Prolog. And that whole process of formal deduction we talked about, well, that's what powers the automated theorem provers that can solve mind-bending logical puzzles. It's a direct line from theory to application.
But, and this is a fascinating but, FOL isn't all-powerful. It has this really interesting built-in limit. The problem of figuring out if a logical statement could ever be true is sometimes undecidable. This means that, for some questions, there's no way for a machine to guarantee a yes or no answer. It's like asking it to solve a puzzle that might not even have a solution. It could just keep searching for an answer forever. So what's the big takeaway here? I think this quote says it best. Just think of first-order logic as the operating system for logical thought in a computer.
It's that foundational software that provides the structure, the meaning, and the processing power for a machine to reason about its world in a formal, structured, and reliable way.
So, we've done it. We've given machines a language for logic, a way to build brand new knowledge from the facts they already have. The only question left is, what are they going to say with it? What new truths will they figure out that we haven't?